with this question, the idea behind it is that in a simulation, you have a trial and you run multiple trials, but a trial is made up of different components. And in this case, we're going to simulate Mateo shooting 5 baskets. So each component is one shot. And when you are choosing how to model this, since you have an 80% probability, since Mateo has an 80% probability of making a free throw, then we want 8 of those digits to represent making a basket and 2 of them to represent not. So the best answer is D. And that's not, so this part right here, is turning it into a binomial problem, but for the simulation itself, it's still going to be, each shot's going to be modeled with an 80% probability. So that's the idea behind that one. Let's look at this one. Ooh, this one's fun, isn't it? All right, you guys have, what was it you meant to be the answer?
C.
You meant it to be C, yeah. And you? Okay, well, you didn't answer C. So let's think about what's going on. Based on the situation that we've got going on, we're trying to figure out if 4 people come up to the counter, what's the probability that at least one of the next 4 will ask for help finding an item? So there's a 1 in 4 probability that someone who comes up to the help desk is asking for help finding an item. All right, so the only way that this condition fails is if all 4 people going up there are not asking for help finding an item. So we need to figure out what's the probability that every one of the next 4 is not getting help finding an item. There's a probability of 3 and 4. And since these are independent events, what we can say is that we can just multiply these together. There's 4 people, so basically it's 3/4 to the 4th power. Now that is the probability that no one is asking for help finding an item. So if we're trying to find the probability that at least 1 is, then that's going to be the complement of what we just found. So it's going to be 1 minus that, and that's the probability of it. Okay. So, fun times. All right, let's look at this next one. So with this problem, a common mistake could be to look at this and decide, well, I don't want these 3 things to happen. So this is actually, well, let's not worry about showing what the wrong ways are. Let's just look at what the right thing is. So the probability, when I say probability of A, that means the probability of A failing, the probability of B, and the probability of C. My goodness, I can't write. C, so that's going to be 0.01, 0.03, and 0.04. So if any one of those happens, the device fails. And so we don't want any of those things to happen, so we don't want A to fail. So what's the probability that it doesn't fail? That's 0.99. The probability that B doesn't fail is 0.97. And the probability that C doesn't fail is 0.96. We want all 3 of these conditions to be true. So we want A to not happen, and B to not happen, B failing not to not happen, and we want C failing to not happen. So because these are independent, we can just multiply the probabilities together. So it's 0.99 times 0.97 times 0.96, which gives you 0.922 when you do that. So the answer is C. Okay.
I kind of did like the last problem. I multiplied like the 3 dots together and then subtracted from 1. What's
What you just found, if you multiply, okay, and that I was going to show that originally. If you just multiply 0.01 times 0.03 times 0.04 and then did the complement to that, what you're finding is the probability that all three components don't fail. But we don't care if all three don't fail. We care just if any one of them doesn't fail. All right, let's see. I don't know how many problems I have for this. Oh man, I have a lot, but we don't have to go through all of them necessarily. So let's just look at this next one. With this kind of a problem, I will say that I think the best way of approaching it is by drawing a diagram. Now we can do a two-way table, but I want to show you with the Venn diagram how it makes sense to me, okay? So there are 78 people in the total population here, the high school science teachers, students. We know that there are some students who are in the band, and there are some students on the sports team. The question is there any overlap between those? Is there anyone who's on the sports team and in the band? We don't know that right off the bat. We need to find out. There might not be any overlap between these two, but let's go ahead and draw it as though there is. So 35 are in the band, and 32 are on the sports team, and it says there are 16 who are involved in neither. So they go outside the two circles. Now, the thing is, if these are mutually exclusive events, there should be no overlap between them, and we can just add up the numbers on the inside, and it should add up to 78, meaning I should add up 16 plus 35 plus 32, and if it adds up to 78, then there's no one who is in two categories, right? But when I add this up, 16 plus 35 plus 32, I get 83. So what does that mean? That means that 5 students are here in this overlap. So what we need to do is to add this up, we can add up all the probability, but then subtract away the students who are involved in both. And the more important thing for this particular problem is that these are not mutually exclusive events. They're only mutually exclusive if the probability of, well, in this case, I'll say B and band and sports has to be 0. But that's not the case because we see 5 out of 78 students are in both band and sports. So they are not mutually exclusive because of that reason. All right. Is this fun? Do you guys miss doing probability more often? All right. Maybe I'll just go through this one real quick because we could have set up the previous problem as a two-way table also and kind of worked through it. So let's kind of look at this. In a certain high school, 17% of the students are enrolled in a psychology course, 28% are enrolled in a foreign language course, and 32% are enrolled in either a psychology course or a foreign language course or both. What is the probability the student chosen at random from the school will be enrolled in both a foreign language course and a psychology course? Well, we don't really need a two-way table necessarily. We need to work with a few different ideas here. The probability of, let's see, psychology or foreign language here, apparently you can be involved in both. So it's going to be the probability of psychology plus the probability of foreign language minus the probability of psychology and foreign language. This is our general addition rule. So we're seeing right now already that 17% of students are enrolled in a psychology course. So the probability of being in a psychology course is 0.17. The probability of being in a foreign language course is 0.28. And it says there's a 32% probability enrolled in either one or both. So basically, the probability of psychology or foreign language is 0.32. So with these numbers, we're trying to solve what's the probability of being enrolled in both of these. So luckily, those are exactly the probabilities that we need for that formula. Again, this is my general addition formula for multiple events. So now let me just plug in what I know. I know the probability of being in either one of them is 0.32. The probability of psychology is 0.17. The probability of foreign language is 0.28 minus what I don't know, which is the probability of psychology and foreign language. So now when I go through and add all this up and do the algebra, looks like I'm just going to skip past the algebra. The probability of being in psychology and a foreign language is 0.13. Okay, very quick overview on that, but I hope it at least reminded you of some concepts. Any questions on that? Okay. Okay, this one's kind of a fun problem too. I'm just going to give you guys about a minute to look at it. In the course of a minute, if you come up with an answer, or maybe I'll give you a minute and a half. If you come up with an answer, great. Otherwise, I'm just going to provide the answer. All right. The events D and E are independent, which means that the probability of D, okay, when two events are independent, then the probability of D and E will equal the probability of D times the probability of E, and no conditional probability comes into play. We already know that this is 0.18 for the probability of D and E, and this is 0.6 for the probability of D, which means the probability of E, we can quickly find out, is 0.3. Now, events cannot be independent and mutually exclusive. So what we have is a situation where when we are trying to figure out, well, we already know probability of E is 3, so we can rule these out because those are not what we're looking for. So now we need to find the probability of D or E. And the probability of D or E, if the events are not mutually exclusive, which in this case, they can't be mutually exclusive because they're already independent. So in this case, that's going to be the probability of D plus the probability of E minus the probability of D and E. So in this case, we have those numbers. It's going to be 0.6 plus 0.3 minus 0.18, which is 0.72.
Wait, so if it was mutually exclusive, then you just do T of B plus T of E?
We would, except in that case, we wouldn't be able to solve for the probability of E, because if they were mutually exclusive, they wouldn't be independent, and we'd have a lot more challenging problem to solve to figure out the probability of E. Okay. And just as a reminder, mutually exclusive means the two events cannot both simultaneously occur. And, or another way, if one event happens, the other one cannot. So flipping heads and flipping tails on the same coin are mutually exclusive events. The idea of independent is that if one event happens first, it doesn't affect the probability of the next event happening. And of course, two events can't be mutually exclusive and independent, because if the first event happens in a mutually exclusive set, then the other one's probability goes down to 0. So they are, by definition, not independent if they're mutually exclusive. Okay, let me see right here. Let me see if this is the best one to do. We have 2 problems left. Let's do this one. This one's going to be more, I don't want to say more fun, but it's going to be better for us to look at. So go ahead, take some time, work your way through this one. With this, there are kind of 2 ways that I can model this. And one of them would be a tree diagram. the other could be just looking at some table of a probability distribution. And maybe I'll just start with the probability distribution. So in the first event, there are three outcomes, I'm sorry. You could get $1,000, you could get $2,000, you get $5,000. Now, the probabilities of those happening, that should have been an X right here. Sorry. So the probabilities is that 1,000 is going to be out of 4 cards. You have a 0.5 probability of this, 0.25, 0.25. All right, so there we are. Now we have another event that is going to be drawing cards, and I can multiply by 2 or just multiply by 1, right? And the probability of each of those, if there's 3 chips are red, so you have a 0.6 probability of doubling your value and a 0.4 probability of not doubling it. Okay, I'm just making sure I'm getting that right. Am I good so far? Everyone agree?
Yeah.
So, huh? 0.4, because there should be 5 chips, 3 are red, 2 are white, so it's a 40% probability for just keeping the value the same. And remember, this has to add up to 1 for all your probability distributions. Oops. Okay, so is that making sense? All right, so now let's kind of think. I can get 1,000 and multiply it by 2. I can get 1,000 and multiply it by 1. So let's do this. If I get I'm going to start from the bottom. Maybe I should have flipped these around at the bottom, but 1,000 times 1, that gives me my lowest outcome. I can get, with X and Y happening, I can get different outcomes, which include $1,000, $2,000. I can get 4,000. I can get 5,000. That's 5,000 and 10,000. Those are the only outcomes that we have. All right, so 1,000 can happen if I have 1,000 times 1, which is going to be 0.4 times 0.5. 2,000 happens if I get 1,000 times 2, or 2,000 times 1. Either way, so it's going to be 0.5 times 0.6, or 0.25 times 0.4. All right, does that make sense where I'm getting those numbers from? Okay, and honestly, from there, I don't need to worry about the rest of the probability distribution, but if I keep going down, like 2,000 times 2, it's going to be 0.25 times 0.4, and then this is going to be the rest of it right here. This will all add up to 100% again. But now I just want to figure out these two. These are mutually exclusive, so I can just add these probabilities together. So I'm going to get 0.6 times 0.5 is going to be 0.3. So if I bring this down, I'm going to get 0.3. And then 0.25 times 0.4 is 0.1. So I'll bring that down. So when I add those together, the probability of getting $2,000 is 0.4. All right. Now, just to wrap this up, we won't look at the last problem. I could have set this up as a tree diagram and said, here are my outcomes, 1,000, 2,000. I'll just kind of move ahead. And then the probability of doubling it, so times 1 or times 2, times 1 or times 2, and then I could have figured out that'd be 1,000 here, 2,000, that would be 2,000 or 4,000, and then of course the same thing for the 5,000, but we can just find the probability of that and the probability of that and add it together. So maybe the tree diagram is a better way of thinking through it. But anyways, that's what you've got. Let me quickly wrap up right before the bell rings. I can't remember if it's 12:50 or 12:55. All right, I did post an Unit 5 FRQ. We're actually not going to go over it till Monday. So, but have a look at it between now and then.
Monday?
Yeah, because we're going to be meeting before then, but just the way it times out, we're not going to be looking at this till Monday.
What about tomorrow?
We're not going to go through anything tomorrow. And then Friday, we're going to be going through what we looked at on Thursday. I had to switch the order up, guys. It's all a mess, but it's the end of the 2020, 2021 school year. Why wouldn't it be a mess? All right. Thank you. If you have any questions, feel free to stick around, but have a wonderful day.